Hello everybody, I will start my today another live coding session. So today I serve this question, is graph bipartite? So in this question, there is an undirected graph with n nodes, where each node is numbered between 0 to n minus 1. Okay, you were given a 2D array graph, where graph U is an array of nodes that node U is adjacent to. Yeah, so this should be the adjacency list. Okay. More formally, for each V in graph U, there is an undirected edge between node U and node V. The graph has the following properties. So there are no set of edges. Graph U doesn't contain node U. Okay. So in the adjacency list, node 1 to node 1 doesn't exist. There are no parallel edges, which means that node 1 to node 2 is connected. There isn't any more duplicated edges. So in the adjacency list, node 1, the list of connected nodes, it doesn't have duplicate, say, node 2. The graph may not be, no. If V is in graph U, then U is in graph V. The graph is undirected. Okay. The graph may not be connected, meaning there may be two nodes U and V such that there is no path between them. There may be two nodes U and V such that there is no path between them. Yeah. So I can say, maybe I can divide the graph into subgraphs, which are, any of which are connected. No, sorry, any of which are not connected. Okay. A graph is bipartite if the nodes can be partitioned into two independent sets A and B, such that every edge in the graph connects a node in set A and a node in set B. A graph is, okay, let me repeat it. A graph is bipartite if the nodes can be partitioned into two independent set A and set B, such that every edge in the graph connects a node in set A and a node in set B. Okay. So it's just like I can, divide each node into two groups, A or B, and every edge connect node from group A and node from set B. Yeah, as written here. Okay, I understood. Return true if and only if it is bipartite. Okay. So let me clarify my understanding first. So as the interface, I'm given the graph, which is the adjacency list. So it should be 2D array. And I will return Boolean, which is a flag if the graph is bipartite or not. Okay. So, okay. As a constraint, one thing I'd like to confirm is if graph has at least one node or not, which is suggested by this. So when I see the constraint, I can find n is 1 or larger. So, yep, which means that there is at least one node. Okay. Maybe in this case, I can think, yeah, it's okay. Good. So let me take a look at the examples. So let's think of the case when something like this, and also another portion which are not connected. Like this. So in this case, the graph adjacency rate should look like 0 is connected to 1 and 2, and 1 is connected to 0 and 2. 2 is connected to 0 and 1. 3 is connected to 4 only, and 4 is connected to 3 only. Okay. In this case, let's say node 0 is in group A. In that case, because node 1 is connected to node 0, it must be from node group B versus a set B. Yes. And also, because node 0 and node 2 are connected, so okay, now I'm assuming that the graph is bipartite and coloring the node, kind of. But if there's a contradict, I can say the graph is not bipartite. But if I can color all of the nodes in a good manner, I can say the graph is bipartite. So I'm thinking that node A and B now is the kind of color. So now node 0 and node 2 are connected. So node 2 should be B. But now node 1 and node 2 are connected, but they're the same color. So there is a contradict. So I should return false. Yeah. And just to be clear, if I start from node 0 with B, the same thing happens. I just completely flip over A and B. Yeah. So in the end, I will find the contradict 1A and 2A. Yeah. So I can start from any group for node 0. Okay. So one more example. Let's say this is not connected. One and two are not connected. So in this case, what happens is that I can color A, B, and then A. Wait a minute. Sorry, node 0 and 2 are not connected. In this way. So now I can say I can color A, B, A, and that's it. No contradict yet. And for 3, I start from A. Obviously, I can start from B. Either is fine. And then node 4 should be B. So I could color all the nodes without contradiction. Sorry. Yeah. So I can return true. Okay. I think actually I came up with the algorithm already, but I'm seeing the example. So colors a node. What should I say? For each node, start from color A. And I will do DFS to color connected nodes as much as possible. What I mean by as much as possible is do DFS to color connected nodes in the same subgraph. Subgraph means that all the nodes are connected, maybe indirectly. Yeah, let me say in this way, subgraph group. So let me say connected group. Then in this process, if there is a, what should I say? Wait, just coloring is not enough. For example, here 0, 1, 2, 0, 1, 1, 2, the coloring is finished. And if I finish here, I can't find the contradiction. So that's a problem. So I have to take a look at each edge. Yeah. To see each edge and color connected nodes in the same connected group. If there is a contradict, or just say if there is the edge which connects the same color, I can immediately return false. Yep. So basically, this is it. Then here I have to do maybe try go back to first step, check for another independent connected group. So this is a case when, yeah, this example 2. In this case, I had node group 1 and node group 2. So after taking a look at node group 1, I have to take a look at node connected group 2, 3, and 4 in the same process. Sorry. Now, in the end, I return true. This is a basic algorithm you can use. So quickly I reduce the complexity analysis. For time complexity, I assume that there are V vertices and E edges, V and E. So assuming this, time complexity should be O of V plus E, because I will take a look at each edge, yeah, exactly once. So it should take at least O of E time complexity. And also, there is a possibility that there is a node which is not connected by any edge. For example, in this case, let's say nodes are there is no any edge between these 6 nodes. In that case, time complexity should be O of V, because still I have to take a look at each node, as I write in line 35. Yeah, because I start from each node, and then I notice that there isn't any edge. So the time complexity should be O of V plus E. For space complexity, let me do it later. Okay, so now let's start the implementation. So let's say color to graph, color to, no, node to color. This is a hash map of node to color, and color is true or false. And there should be n nodes And for each node I will check if if it's already colored. If this is already colored, I can skip. Otherwise, I start coloring from here and color all the nodes in the same connected group. So I define the helper method here. And yeah. Here, I have to take care if I can color all the nodes without any contradiction. And if there is a contradiction, it's the end of the, it end of the coloring. I can just return false from the main method. So if I can color without contradiction, I will return true. Otherwise, I return false. So, and in this way, in the main method, if I couldn't color all of the nodes, I return false immediately. Yep. Then in the end, I return true. Okay, and something I have to take care is when I color the nodes, I have to append the new node into this node to color. Because this node to color is also used as a kind of business set. So with, this, wait, yeah, this is used as a business set in the main method. So I have to, give this node to color hash map to the helper method and mutate it inside of the color nodes method. Yep. So that being said, I start implementing the helper method. Oh, and I need start node. And also I marked the start node. Yeah, actually false is fine too. It doesn't matter. Okay. Here I do the DFS. So I will take a look at each node. Okay, and there are two cases. Number one, this current node is already visited. In that case, I have to check if there is a contradict or not. Number two, if this is already visited, sorry, I check contradiction. If not, out of this. Yeah, so this is what I like to do. So prev color is node to color prev. Current color is node to color current. If they're not the same, return false and finish immediately. Otherwise, so otherwise, current is, yeah. Otherwise here in line 81, I don't have to do anything. I just could confirm that this edge doesn't cause any contradiction. It's okay. So in line 82, in this else case, so what I would do is color this. Yeah. So prev color is this one. Let me move it here. So node to color current is not prev color. Yep. I just flipped the Boolean flag of the color. Okay, so I've colored it. Yeah, that's it. So now I could handle this edge connecting previous to current. Yep, good. And I think I have to append this current to stack. Wait, but I think it is the case only if I color this. Yeah. Okay, and I keep doing it, and in the end, return true. Okay, so I finished the implementation with the helper method. Let me quickly check. In line 68, I color the start node and I push into the stack. I don't need the visited set because node to color hash map works as the visited set. And in line 72, I pop out the node element from the stack. And in line 73, I take a look at each edge from this node. And for each adjacent node, if this is already visited, I check the contradict and return false if there is a contradiction. Otherwise, I just color this and push into the stack. In this way, the one node is pushed into the stack exactly once. And for each edge, from that node, they're checked exactly once in line 73. Yeah, this is good. Okay, let me quickly dry run my code. So I will use the case when. So I have two test perspectives. Number one, if there is a contradict, I can find that out. And if there isn't, I don't find it out. I should return true. With me. For example, this case, this should return true. For this case, this should return false. And as a case, I try to check the multi-connected group checks. This is a second perspective. Maybe this one should be better. Yeah, but I think I don't have so much time to do all of these test cases with dry run. So I pick up this case only. Yep. So in this case, n is 3. So node to color is initiated with empty hash map. And then line 76, firstly node I is 0. In this case, I is not a node to color hash map. I go to line 79 and I will call color nodes. Now start node is 0. So start node is not in node to color. Yes, so I go to line 91. And node to color 0 is true. So this is appended to the hash map. And in line 92, stack is as only 0. Yep. So in line 95, I pop up this as a prev and graph prev. The graph prev. So actually, this is. I will copy paste this. Where is it? So I was talking about line 99 because prev is 0. This is 1, 2. So current is node 1 and prev color is now. Wait. I can take a look at this here. Prev color is true. So for node 1 is not in node to color. So I go to line 108 and node to color current, node 1 is reverse color of prev color, which is false. So 1 is now false. Okay. And I go to line 109 and push this node 1 to stack. Okay, and I come back to line 100 and I will take a look at node 2. So node 2 is not in node to color yet. I go to line 108 and again, the same thing. Node 2 is colored as false and I push it into the stack. So I come back to line 98 and prev is now 1. Prev color is now false. Current graph prev is node 1 is connected to node 0 and 2. Yeah. So for node 0, this is already visited. I go to line 103. The current color is node 0 color, which is true. Actually, prev color prev color, which is false, is not current color true. So in line 105, I return false. So when this is false in line 82, yep, and 83, I return false. So in the end, this returned false. Okay, I passed this test case. So with this dry run, I could cover almost all the lines except for line 111 and also line 81. And I'm basically pretty confident in my code, so I will submit. Length. Start node is not defined. Yes, this is I. Maybe I can just say start node here. This is more clear, I think. Typo. Oh. Seems like there is a mistake somewhere. Let me check. So node 0 is connected to 1 and 3. Node 1 is connected to 0 and 2. Node 2 is connected to 1 and 3. And node 3 is connected to 0 and 2. Yes, okay. It looks like this. And this should be true, yes. There's no contradiction. But it says there's a contradict. Let me check what happens. I color with 0 true, 1 false, 3 false, so for good. And after that, what I'm painting now. I was trying to paste node 0. I mean, when I'm coloring node 0, I have a contradiction with node 3. I think I'm coloring the same color maybe. Wait. Okay, so I think this isn't a good idea for debugging. Maybe I will think, from the upper, yeah, upstream. So I find the contradiction in the first node coloring, not node 0. So when I paste node 0, when I color node 0, let's see here, colored. And also here, initial colored. So initial color is 0, 2, and colored 1, 3. Colored 1 with false, yes. Colored 3 with false, yes. And basically this is it. But somehow I'm trying to coloring 0. Okay, so I, messed up the video shooting, so I take it again. So I add, what should I say? So I add another print statement here. Here. So now I can see I'm checking 0 to 1, and now 0 true and 1 false, yes, and 0 to 3, and I find true to false, yes. Then I check 3 to 0, and 3 is false, and 0 is true. But there is a contradiction. And I noticed that the problem here is prev color is not current color. This is expected pattern, expected case. But if there is the same, I can say there is a contradict. Yep. So in this case, this is true, false. They're not the same color. So this should be okay. That's the problem I had. And now accepted. Okay. So I will submit my code. Good. Okay, that being said, I finished the space complex analysis. I left. So there are two data structure I used: color to node hash map, and also I use stack. For color to node hash map, if there isn't any contradiction, I add each node into this hash map, and the value is Boolean. So there should be over V time space complexity. For stack, let's think of the case when one node, initial node, is connected to all the different nodes, remaining nodes. In that case, initially, from the first node, every remaining node are pushed into stack. So the stack contains V minus 1 nodes. So there should be over V space complexity. So in total, it should be over V. Okay, that being said, I quickly wrap up. So today I solved the question, is graph bipartite? So the definition of bipartite is that if the graph, what should I say? I try to divide the nodes, each node into two groups, A and B. And every edge connect node from group A and node from group B. So if I can divide the nodes in that way, which meets this condition, when dividing into A and B, I can say this graph is bipartite. Yeah. So my task was to find out if the graph is bipartite. Yeah. Okay, that being said, the algorithm I used for this question was that I start from specific node and color that node with true, or I should say color that node with black. And I do the DFS and color all the connected node to that, maybe indirectly. So if the node is already colored, I just check if the edge I'm currently looking doesn't cause the contradiction. If the color is not, sorry, if the node is not colored yet, I color the node with the inverse color of the another node connected to that node. Yeah. And I do that from one specific node. And after finishing it, I work on the same thing for another node, which should not be connected, even indirectly, to the previous node. I do repeat it, just like I written here. Yep. So that's the algorithm I used for this question. Okay, that being said, I finished my today's coding practice. Thank you so much. Bye.